Hi everyone. In this video, we're going to continue our discussion on sampling distributions, and specifically we're going to actually talk about the first, I said there was two ways to sort of get at these sampling distributions. We're going to talk about the first one, which is to use probability rules in order to get them. Okay, and so also if you hear weird noises, my dog is playing with his toys in the room, and so that'll be him crunching his toys. Okay, so anyway, there are some situations in which an exact sampling distribution is available, so we're not actually going to need to know all of our probability rules that we talked about in the first 3 or 4 chapters, but we are going to make use of some of that knowledge. Okay, and so we're going to focus on 2 sampling distributions, and this is going to get us all the way through the course, basically, or at least through a lot of it, the next couple weeks, and that is the sampling distribution of a mean and of a proportion. Okay, and so there are some symbols that are required, or that I'm going to use in these videos, and I think it's going to be helpful if we write them down now. The symbol for a population mean is mu. Okay, and so we've seen mu before, but mu is a population mean. Okay, and its sample version, so we talked about the difference between a population and a sample. The sample version is x with a bar over top of it, and that's pronounced x bar. And that is the sample mean. Okay, so that's the sample mean. And then a proportion, and so if we I think everyone knows what a mean is. A proportion is the part of a whole. And so, in a sense, if I interviewed 100 people and 58 of them believed something, then the proportion of people who believed that thing, whatever that was, is 58 out of 100. So it's like, it's a percentage. A proportion is a percentage. And so you can sort of think of proportion, percentage, and probability are kind of the same, in a sense that a proportion can be between 0 and 1, and it's they're going to interchange in a sense throughout. Okay, so a population. So we also have population and sample versions. The population proportion we're going to call P. So that's the proportion in the population, and then the sample version is going to be P with a hat over it, and we call that P hat. All right, so that is the sample proportion. Okay, so those four symbols are going to get you a long way in these videos, and they'll be important to remember. Okay, so we're going to start with a sampling distribution of the mean, and specifically we're in section 5.4. Okay, we're in section 5.4, I believe, which is called sampling distribution of the mean. It turns out, and this is maybe a little more technical than you need, it turns out that you can look at, or you can view a proportion as a mean. Okay. We get the population mean by adding up, say, if we have x points. So if we have like x1 plus x2 plus x3 plus x4 divided by plus all the way up to x sub n divided by n. That's how I get a population mean, right? I add up all the numbers and then I divide by how many numbers there were. That's a mean. A proportion is essentially doing the same thing, but now each person is assigned either a 0 or a 1. And it's a 1 if it does happen, if that person is a success in some sense, and then 0 otherwise. And so we're doing the same thing. We're adding up all of those numbers and dividing by the total again. It's just that these numbers, x1 or x2, x1, x2, all the way up to xn, can be either 0 or 1. And so sometimes people call that an indicator variable. It's either on or off. Okay. And so essentially a proportion is the same thing as a mean for this. And so that's why we're lumping them together, because the theory behind it is the same for either. Okay, so let's move on to actually looking at this. So we want to look at the sampling distribution of x bar. So x bar is our statistic that we are interested in sampling, okay? And we're going to look at the sampling distribution of x bar, and it turns out there's some pretty powerful theory behind this that says that x bar is almost always going to be normally distributed. And so I'm getting a little bit ahead of myself, but that's where we're going to go. So the sampling distribution of x bar actually depends on the sample size n, okay, which we know from our experience of simulating sampling distributions, especially with with the project that you're doing. You're going to find out that n really matters in different circumstances. Okay, and so that's important to note. And there's actually two different situations which we need to break up the sampling distribution of x bar into. And the first situation is when when the data, the population, is normally distributed. Okay, so maybe instead of data, I should say the population is normally distributed. So, right, we need a population to sample from. If that population is shown to be normally distributed, okay, with some mean and some standard deviation, okay, then we know exactly, there's some theory that we can, or there's some like probabilistic algebra that we can do to say, sorry, let me get rid of all this that I wrote down here. If the population is normal, then x bar, the distribution of x bar, is also normal. Okay, so x bar is also normal. So we would read this as x bar is distributed as a normal distribution with mean mu and standard deviation. So this is the mean of a normal distribution. Okay, and this is the standard deviation of the normal distribution. And it's sigma over the square root of n, okay, where sigma is the population standard deviation. Okay, so there's a relationship between the population and its parameters, or its how it's described, or how it behaves, and then how the sample is going to behave as well, which shouldn't be surprising. Okay, the sample was taken from the population, and so it should sort of depend on the population in a sense. Okay, so we have that if x is normally distributed with mean mu and standard deviation sigma, then we have that x bar is normally distributed as well with the same mean, so it's centered at the same place, and then its standard deviation is a little bit different. Again, it depends on n, and so we're dividing by the square root of n in the standard deviation because of reasons. Okay. Now, the second situation is when x is not, when the data or the population is not normally distributed. Okay? It could be exponentially distributed, it could be gamma, it could be Weibull, it could be anything. We could not know what it is. Right? When the data is not normally distributed, then we have this. And so if you look here, you'll see that, we'll see that these two functional forms, or these two like distributions, are almost exactly the same. Okay, so it turns out that it's going to look almost exactly the same no matter if it's normal, or whether the population is normal or not normal. Okay, it's going to end up pretty much the same thing. But the one difference here is that I've got two squigglies instead of tildes, instead of one tilde. Okay, and two tildes, one tilde corresponds to is distributed as, and two tildes is approximately distributed as. And now the difference may not seem large to you at the moment, and in sort of practice and how we interact with this in the course, it's not going to be that different. But the theory behind it is extremely important. Okay? And so we need to understand the difference. And the difference is that this is always true no matter what n is. That top one, when the population is normal, that's true always. The bottom is only true when n is large enough. When n is large enough. And specifically, the rule of thumb is that when n is greater than or equal to 30, then this is true. Okay, and this is due to something called the central limit theorem. Okay, so this is extremely important. That's the difference between approximate. The top is always true. The bottom is only true if this is true. Okay, if the sample size is greater than 30. Again, you'll see this in the project. Okay, so you'll see this in the project. I built it into the first part of the project that you sort of explore this in a sense. Okay, so these are important things to write down because you will use it a lot. Okay, not just thinking about it, but you'll actually use this a lot. Okay, so now it's important to sort of describe what this central limit theorem is. Right, so we haven't interacted with a lot of mathematical theorems or statistical theorems in this class, but this is probably the most important theorem in statistics. And it's actually a class of theorems, and theorems are things that are like known to be true, and no one questions them because they've been proven to be true in a sense always. And it's a class of theorems that say something about how averages behave, how means behave. A mean is an average, okay? And so it controls how means behave. And both the sample mean and sample proportion are averages and fall under the central limit theorem. So that's what I've been sort of saying here. And it turns out there are many different central limit theorems. We are going to use one called the Lindeberg-Levy central limit theorem. Okay, so that's just some things about the central limit theorem. How you're going to interact with the central limit theorem are going to be these predications on which the sampling distributions are true. So if I go back and say we see this, okay, that bottom thing is only true when n is greater than 30. So it says if the sample size is large enough, then the distribution of means is normal. Okay, that's what the central limit theorem says, basically. And so n greater than 30 comes from that central limit theorem. Okay, so hopefully that wasn't too bad to think about. Now let's actually do an example of finding the sampling distribution, and then even further using that sampling distribution to find probabilities. So doing what we've been doing in chapter 4 in a sense. Okay, so according to the 2010 Census Bureau current population survey, the average number of people in a family household that contain both family and non-family members is 4.43 with the standard deviation of 2.02. Okay, so suppose I take a random sample of 225 people. And so the first question I'm going to ask is, what is the sampling distribution? And the second one is a probability question. What's the probability that I would see a mean of at most 4.2? So first we need to find the sampling distribution of X bar. Okay, this question is about means. Okay, so this average number of people is 4.43. Standard deviation is 2.02. I'm interested in means, specifically X bar. And so we have to ask ourselves, are we in situation number 1 or are we in situation number 2? Is the population normally distributed or is it not? And unless the problem says the population is normally distributed, then we say no. And if you look here, it tells me a mean and it tells me a standard deviation, but it does not tell me that the population is normally distributed. So I have to assume not. And so the distribution, the sampling distribution of X bar is going to be approximately normally distributed with the same mean, 4.43, and a standard deviation of 2.02 divided by the square root of 225. Okay, and that's true if n is greater than or equal to 30. And so is 225 greater than or equal to 30? You bet it's much larger, so that's good, great. If that's true, then we can say this. And because it is, now we have a sampling distribution for X bar. That's important because now I can ask a probability question about X bar. I ask, what's the probability that I would see a mean of at most 4.2? And so that's the probability that X bar is at most, which means less than or equal to 4.2. Okay, and again, my dog is now snoring in the background, so if you hear snoring, that's him. We know that X bar is normally distributed, okay, and we're interested in a probability question. So all we need to do is pull up Minitab, okay, and then enter in the numbers. So we just need to calculate what is 2.02 divided by the square root of 225, okay, and then we just enter in the numbers. This would be a cumulative probability question, okay? And so I don't have Minitab up right now, and so I'm not going to actually calculate this probability, but I will go over it in class, okay? So you can do this, and then we'll check our answer. And along the same lines, I have a your turn. Okay, and I'm going to ask you the same type of question. Suppose it's known that the distribution of GPAs at Shippensburg has a mean of 2.9, standard deviation of 0.35. I take a sample of 200 students. Okay, what's the sampling distribution? What's the probability I see a mean of at most 2.75 from my sample of 200 students? Okay, all right, so that's that. We'll come back next time and look at the sampling distribution of p hat.